Take the opportunity to thank Indra Nil again for organizing this week. Unfortunately, I can't stay for the next week, but it was really great to be here, and it was a really nice opportunity to give all these talks. So I really appreciate it. Okay, so during this week, we've seen that that harmonic maps can be used to get restrictions on fundamental groups of Kaehler manifolds. And they also have an application to Higgs bundles through the non-abelian Hodge theorem. And so today I want to, so those are harmonic maps to symmetric spaces. And so today I want to talk about harmonic maps to more general metric spaces. And so again, I want to give one application due to Gromov and Chern to fundamental groups of Kaehler manifolds, and then I'll give another application to Higgs bundles as well. So the plan of the talk is to start by describing what I mean by a harmonic map to an NPC space, so non-positively curved metric space. And then I'll give some sort of a relationship here with compactifications of character varieties. And then the third one will be the Higgs bundle application to what I call representations with smooth spectral data. Okay. So first of all, let's talk about maps to NPC spaces. So as motivation, this sort of comes in from two different directions. So suppose I, again, am in this situation of a Riemannian domain, but this will be a Riemannian domain, but now we want to generalize the target. So what is one motivation for this problem? Well, it was originally, I guess, an idea of Gromov, and then worked out by Gromov and Chern, that developing this theory to general NPC spaces could be used to prove superrigidity type theorems. So they use this to prove it's called p-adic superrigidity. And the subsequent arithmeticity of lattices in quaternionic and Cayley hyperbolic symmetric spaces. So this was in some sense, the original idea of Gromov for this. In another direction, sort of more of a formal, foundational kind of direction. So remember that the way I phrased it for Riemannian targets here, we wrote down Euler-Lagrange equations in local coordinates. So there was some PDE in local coordinates involving Christoffel symbols, et cetera, that harmonic maps satisfy. So if one wants to look at general harmonic map theory, and in particular to non-positively curved targets, then you have to go through, as usual in analysis, you have to go through the whole process of weak solutions, et cetera, and introduce Sobolev spaces. And so that's fine, but in this problem, it makes no sense, because to write down this equation, I have to assume that my map is mapping into some coordinate patch where I can write down coordinates. And it doesn't really make sense to say that a map in some Sobolev space lies in a coordinate system like that. In general, it's not true. So we got around that problem by using this flow and only dealing with continuous maps. So this made perfect sense. But that's a problem in general. And so what people normally do is they use the Nash embedding theorem. So they normally embed n into some isometrically into some big Euclidean space, and then they write down the corresponding equations for a map to lie in n and satisfy the harmonic map equations, and then now you can write this in a global way and talk about weak solutions. Okay? But somehow this is maybe, I don't know, you're using kind of a big theorem to just get the whole problem started, and it seems a little bit unnatural. And so Korevar and Chern and also independently by Yost, sort of developed an intrinsic L2-1 theory. Intrinsic theory of Sobolev mappings. And that's the one that's going to make sense now in the case where you have more general MPC targets where you don't have any sort of isometric embedding into Euclidean spaces. So let me just briefly give you an idea of what this is all about, okay? And so today is going to be very, very few details, but what is the general idea? So let's let N now be an NPC space. So this stands for non-positively curved. So it's just a metric space. For right now, I'll just work locally, and then I will talk about an equivariant problem in a second. But right now, this is all just very local. So, so of course, now I'm going to say it's a complete metric space, so that doesn't sound very local. But what is the general situation here? So this is a complete metric space with the distance between any 2 points realized by a unique rectifiable path. And we impose this non-positively curved structure in terms of triangle inequalities, or triangle comparisons. So if I have 3 points, in my NPC space N, and I look at the corresponding Euclidean triangle over here with the same length, then I want to measure the distance between, say, P and the midpoint of that other geodesic, and that should be less than the distance of the corresponding point over here. So it's more negatively curved. It's at most as negatively curved as Euclidean space. So that's the way you define NPC. Okay, so now we want to talk about so how are we going to define a harmonic map? So we have to first of all talk about the energy of a map from X into this NPC space. So how do we do that? So we'll say that first of all, a map, and again, maybe the appropriate way to do this would be to say, let me just take an open domain inside of X for the moment, and I'll keep this target to be a complete NPC space. And so here, this will be L2 if, so this will be an L2 if the integral over omega of the distance squared, say, from any point of u of X is bounded. Okay, so there will be a notion of saying that a map is an L2. And you can check in all of the things I'm about to say that when the target is a Riemannian manifold, these are equivalent notions. And then now we want to talk about L2-1. Okay, so we need one derivative to be an L2 as well. So how do we do that? We do that by using ball averages. So let me define, let me do it over here. So L2-1. So first of all, I'll define the energy density depending upon some epsilon at a point X, the approximate energy density, and this will be the average, sort of the ball average. Take the ball of radius epsilon dot X, and then take an approximate derivative. And integrate with respect to the surface area along Y. Okay? So this is sort of an approximate derivative integrated around the surface surrounding this point X. And so if U is in L2, then that implies that this approximate energy is in L1 as a function on x. And so in particular, it defines a map. It defines a linear function on all the continuous functions. So a map on the continuous functions, say, I guess with compact support or something, on omega into R. Okay? By integration. And so now we define the following. So here I better use my notes, otherwise I'll get something wrong. Oh yeah. So let me give this a name. E epsilon of u. Okay, so it's that linear functional defined by this approximate density here. And so then the idea is that we let EU be the sup over all functions. And then I take the lim sup as epsilon goes to 0 of this epsilon evaluated on phi. Okay. So of course that could be infinite. And when it's not infinite, then we say that U has finite energy. Okay, so U has finite energy. This is the finite energy condition. Okay, so that's rather technical, but I just wanted to show you what the definition is, right? It's done by taking sort of these kind of metric space approximate derivatives and then defining things rather measure theoretically in some sense. Okay, and so the key proposition by Corvar and Shane is that if U has finite energy, then the energy density, so this E epsilon U x the volume of x at the point x, okay, as a measure, this measure converges weakly to a measure which I'll call EU, the volume of x. And to write it like that is already implying the statement of the proposition, namely that this converges weakly to a measure that's absolutely continuous with respect to Lebesgue measure. Okay, i.e., there's a well-defined energy density. EU, which is a local L1 function. And this plays the role of the norm squared of du. But this is not necessarily the square of anything. It's just the energy density. And so this is kind of the key proposition that makes everything start to work. Okay? And so Corvar and Shane go on and now talk about harmonic maps. And they prove many results. And so let me just state kind of the key ones. I think I've got enough room here. So here's kind of the sort of the highlights of the theory. So the first one is certainly the most important one. So so first of all, I should say they prove the existence. Okay, so let me put it in here. So there exists a unique solution to the boundary value problem for U into N. So I for the Dirichlet problem, so I specify a map on the boundary. I choose a suitably nice domain here, and I can solve the Dirichlet problems where U is an energy minimizer. So first of all, there exist maps of finite energy, and then moreover, with respect to this Dirichlet problem, there exist energy minimizers for that. And the one thing that we know about this is that it's Lipschitz.
with a constant that depends on like the square root of the energy. Okay? So interior uniform Lipschitz continuity with a constant that depends on roughly on the square root of the energy. Okay? So that's kind of the main result, is that this whole theory is good enough to talk about energy minimizers, and they are at least Lipschitz continuous, which actually is the best you can hope with what I've said here, because the target is just an arbitrary metric space. So they also talk about the equivariant problem. So, so suppose that rho is a map in the isometry group of this NPC space, and suppose either
so let me get the statement absolutely correct here. Yeah.
So suppose that rho of pi 1 has no fixed point on the Alexandrov boundary of this NPC space. So the Alexandrov boundary is the equivalence classes of geodesics. Okay. Has no fixed point on the boundary. By the whole image of this group, yeah, exactly. Then, if either n is locally compact, you see, I'm not assuming n is locally compact, and in some sense, part of the applications that they wanted to study were the case where n was a Hilbert space. So n could be very big, right? But for this problem, either assume that n is locally compact, or it's cat minus kappa for some kappa bigger than 0. So what do I mean by this? I mean that when you do the triangle comparisons, you replace Euclidean space by hyperbolic space with constant curvature minus kappa, and do comparisons there. So if you have strict negative curvature in some sense, then there exists a rho equivariant energy. Okay, so this is very similar to the Corlett theorem, right? Because this is like the semi-simplicity in the Corlett theorem that we assumed. The only thing is that that's not quite good enough in the case where the target is like a Hilbert space or something. And so if you really want an existence theorem, you need a little bit more. I think that's right. I think it doesn't quite apply to that case. And in fact, that's probably very much related to property T. Yeah, exactly. So, yeah. Okay, so I think I don't have enough room for the third thing here, and the third one's kind of important, so let me do it somewhere else. So the third property is a strong compactness theorem. So specifically, suppose I take a sequence of energy minimizers. So this can be either the equivariant problem or the Dirichlet problem or whatever. So let's, I'm going to use it for the equivariant problem. So let me think of the equivariant problem. And where I have a sequence of, I also allow the spaces to vary as well. Okay? So here I'm going to apply it for a sequence of representations where the space is fixed, but the representations are changing. But in any case, this is very, very general. So suppose that these are energy minimizers. I should take this away. So let me just. And suppose that there is a uniform. So with a uniform modulus of continuity. So I won't say what that is, but it's basically sort of uniform Lipschitz property. Then there exists a convergence subsequence. Ni to n infinity, where this is convergence in the Gromov-Hausdorff sense, and an energy minimizer u from x to n infinity, u infinity to x infinity, and these maps converge also in the Gromov-Hausdorff sense. So there's a notion of Gromov-Hausdorff convergence of maps as well as spaces. So Ni is a sequence of NPC spaces. So the only thing I'm fixing is the domain. And I just take a sequence of NPC spaces and I assume a uniform bound in the energy, first of all. So either I'm thinking about the equivariant problem or maybe I'm fixing a domain. So uniform energy bound and a uniform modulus of continuity. And then the statement is that there exists a convergence subsequence of the Gromov-Hausdorff sense. And moreover, there's no loss of energy. So the energy, the total energy of U infinity is the limit of the energies of the UIs. Okay, so that's also a key property. If you take x to be a point, well, you get a point. Yeah, and infinity is a point. So this is really Gromov-Hausdorff. I should maybe clarify. This is really Gromov-Hausdorff convergence of the convex hulls of the images. So in other words, the rest, where the part of n where the image of U is away from that part I don't care about. I'm only interested in the image of U. And since it's an energy minimizer, right? So I've got this nice convex set. So it's a convex set, the image, because it's an energy minimizer. And so it's really Gromov-Hausdorff convergence of the convex hulls of the image. Yeah. No, that's the thing, is that I'm not fixing base points. So this limit I will call the Corvar-Shane limit. Okay, so let me reserve that because I'm going to come back to it later on. Okay, so that's kind of just a really very brief introduction to what Corvar and Shane do. And now earlier, Gromov and Shane. So this is kind of a generalization of what Gromov and Shane did. So Gromov and Shane considered a certain class of locally compact NPC targets that are actually simplicial complexes. So Gromov and Shane considered the case what are called F-connected. Again, this is just some technical point that there's no point in really explaining. F-connected simplicial complexes. NPC simplicial complexes, and they proved a regularity theorem in that case. So they proved a regularity theorem, namely, well, let me state it in the way that I'm going to use it, because I'm sort of going to run out of time otherwise. So suppose that U is X was just Riemannian. So now I'm going to assume that X is Kaehler. So suppose that omega is inside of X, and this is a Kaehler manifold. And this is a harmonic map, an energy minimizer. So here I'm I'm using energy minimizer and harmonic interchangeably. So harmonic for some fixed Dirichlet boundary conditions. And here n, this n is one of these F-connected simplicial complexes. So it's just a simplicial complex that's sort of in a sufficiently nice kind of a form. Then the statement is that U is pluriharmonic. So this is like the Simpson theorem. So of course, before I said that, I should have said something about the singularities. What does that mean? So the singular set of U has codimension at least 2. So what do I mean by the singular set? Well, this is a simplicial complex. So of course, if I'm mapping a portion of omega into a face, then that's just a Euclidean space, and it's just a usual harmonic map, and you expect that to be a smooth map. But now you might worry about what happens when you try to go over edges and vertices and things like that. So the statement about the singular set means that away from this codimension 2 set, locally, around every point, there's a ball that maps into a face. Okay, so it's just an ordinary harmonic map into Euclidean space, so therefore it's smooth. So that's what I mean by the singular set, is this set, essentially the pre-image of the vertices and the edges and so on that you're crossing. So let me try to motivate this a little bit. So there's a beautiful thing that you can find in the introduction, actually, of Gromov's chain, and this is also going to be relevant. So let's take the surface case. Let's just assume that X is a surface. So here's a little disk in the plane, and maybe I've got a simple tree like this, or a portion of my tree, which looks something like this. And so then maybe I'm in a very good situation where the map is sort of taking, the corresponding thing down. Okay? Now, so what's happening with this map? So I'm going to fill in a way that's kind of harmonic. And so what you see is that, say, like this portion here, where does all of that go? So that's going to go onto this segment here. Okay? But that's just an interval. Right? And so this is just an ordinary harmonic function on this piece. And similarly over here, this portion is just going to map onto the segment that goes the other way, which is, again, just an ordinary segment in the real line. And so I've just got an ordinary harmonic function on this piece. So the only place where I have problems and possible, problems with differentiation and things like that is at this point, which goes to the vertex. There are other points that go to the vertices, but in terms of the map, they're actually smooth points because, so there might be a point over here that maps to this vertex in the tree, but it's a portion of this segment, and so it's differentiable. Okay? So this is the idea, and this point has codimension 2. So this rough is the way you can imagine that maybe something like this is plausible. Okay? So of course it's very, very hard to prove, but I mean, very hard. It requires a lot of analysis to prove this, and that's the whole first part of that paper where they do that. Okay, and once you do that, then what you can show is that U is pluriharmonic in the sense that one gets a holomorphic quadratic differential on X, on omega. Okay, so well, in some sense, it's yeah. I was wondering about that myself. In some sense, I mean, it's kind of Euclidean space. I mean, it's not. Yeah, I think there is. I think somebody smarter than me can probably answer that question better. But somehow the kind of F-connected simplicial complexes that they're looking at are Brouat-Titz buildings, and these are like different avatars of symmetric spaces in some sense. And so symmetric spaces we know have non-positive complexified sectional curvature. So in some sense, that's why you would expect something like this to be true. But the actual proof is really just a little bit simpler. It's just using Sue's argument and this regularity theorem. Okay, so let me give you an application. Here's a theorem, which is an application of this, and this is again due to Gromov and Schoen. So let's let X be a compact Kaehler manifold. And suppose that the fundamental group has an amalgamated free product decomposition. And here I think I need to assume that this subgroup here has index at least 3 in one of the two factors. Okay. And that's it. And then the statement is X, then there's a surjective holomorphic map from X onto a curve. So this is a projected curve. And moreover, pi 1, some finite index subgroup of pi 1 of X surjects onto a surface group. By surface group, I mean something of genus bigger than 2. It might be not that curve, but possibly something else. But surjects onto a surface group. So this puts restrictions on Kaehler groups. So probably Sean can come up with an example of a group of this form that doesn't have a surjection onto a surface group. And so those cannot be Kaehler groups then. I think the Higman 4 group is one example. But, you know. And where does the proof of this come from? So here, there's a tree associated to this. So this is the Bass-Serre theory. That whenever you have H and N extensions or amalgamated free product extensions, there's some simplicial tree with an action of the associated group. And so one takes the harmonic map and has pluriharmonicity and gets a quadratic differential and looks at the leaf space of that, and that's what's giving you this projection. So this is a rather long argument. I should also put Simpson's name here. He did it independently as well. But anyway, this is an application of harmonic maps to trees. So this is a tree, which is a special case of an MPC space. So this is holomorphic. The second one, yeah. So what happens is, so strictly speaking, if I think of this, yeah. So strictly speaking, what they prove is that so here C is H2 by a co-compact Fuchsian group, but this guy might have torsion, exactly. So that's what's happening. And so this finite index subgroup is the one that makes that torsion free. Yeah. Okay, so, right. I have to hurry up here a little bit. So in this case, the relevant NPC space here is a tree. So a simplicial tree, which I'll call a Z tree, actually. And that's an example of an MPC space. In fact, it's cat minus infinity because all geodesic triangles are completely degenerate. And so it's got as negative curvature as you like. So that's a little bit funny. A tree is either flat or it's got curvature minus infinity. And actually, for our purposes, the curvature is minus infinity. So, okay. So trees come up in lots of different, trees had come up previously to this as well, in the context of character varieties. So that's the next topic. So here, let's let gamma just be a finitely presented group, actually finitely generated, I guess is enough, but let's say a finitely presented group, and here I'll call m Betty of gamma will be the, let's say the SL2C character variety of this guy.
Okay.
So then I can assert, so if I have a point in here, so I'm going to take a representation, I can define a length function. So for gamma, in gamma, I'm going to define the length to be the inf of the translation distance. So x in H3, the distance in H3 between x and rho gamma of x. So here, notice that H3 is the symmetric space that we've been talking about before. So this is sometimes called the length function associated to this guy. And so the Morgan-Shannon compactification is a compactification of m Betty where we take limits. So here, let me just say that this gives me a function on, let's say, the space of conjugacy classes in gamma. So this is conjugacy classes. Okay, so associated to a representation, I get a function on conjugacy classes, R plus, I guess. And so the Morgan-Shannon compactification compactifies the space by looking at projective limits of these guys. Takes projective limits of length functions. And what they show is that the length functions that appear in the limit, the limiting length functions, are the translation length functions for an action of gamma, an isometric action. Oh, you can't read this, sorry. For an isometric action of gamma on an R tree. So an R tree is well, it's an NPC space, it's a cat minus infinity space. It's not a Z tree because here you're not assuming it's locally compact. So you could have very, very wild kind of neighborhoods. And so these limits are not necessarily simplicial trees. More generally, they're R trees. So this looks very ad hoc or whatever, but it actually comes from, again, this Bass-Serre theory and earlier work of Color and Shalin. I should put here. Which constructs a tree. So Serre has a tree associated to SL2 in some field with a discrete evaluation. And so in the case where your character variety sort of magically is an affine algebraic curve, for example, then we get an element in here on the function field of the curve, and we have discrete valuations for the points at infinity. And those trees are exactly the trees that are appearing in Morgan-Shannon compactification. Okay, so I'll call these limits Morgan-Shannon limits of representations. Morgan-Shannon limits. Okay, so now let me state a theorem then. I wanted to say a few more words, but So let's look at this, this situation. So let's suppose that we have X is just a compact Riemannian manifold. And I have rho I. A sequence of representations in SL2C of the fundamental group of X. And I can assume, since I'm really thinking about the character variety, I can assume that these guys are semi-simple. Okay? And suppose that rho I goes to infinity. So in other words, there's no way to, by conjugation, make these converge to a representation. Then we have two limits. Namely, there is a well-defined, so there exists an action. There's a Morgan-Shalen limit, i.e. an action on an R tree with some length function, L infinity, say, so that the length function of rho I subsequently and projectively converges to this guy. So it's a projective limit. On the other hand, there's a Corvar-Shane limit. So I also have harmonic maps by Corlet's theorem. There exists rho equivariant harmonic maps. It turns out that if these representations are diverging, the energies of these maps also diverges. And so I have to rescale the target space by numbers to make the energy finite. So maybe I'll write this as HI rescaled, and now I'm gonna mess it up if I try to remember the rescaling, but it's by the square root of the energy. So I guess I divide by the square root. I want the curvature to go to minus infinity. So anyway, so we rescale H3 by the square root of the energy of the U1. Okay? And then we obtain from this a Corvar-Shane limit. And so here's a theorem then. So this is Daskalopoulos and Gostolo and me. Daskalopoulos, Gostolo, and me. So then the Corvar-Shane limit is a harmonic map to a tree whose length function agrees with the Morgan-Shalen limit. So i.e. the KS limit is the same as the Morgan-Shalen limit. There's a slight subtlety here because the length function doesn't completely determine the tree always. But modulo that little caveat, then the trees are actually, the minimal trees are actually isomorphic. Okay, so yeah, so in the case where this length function is not abelian, there's sort of a unique minimal tree that has that as its length function. No, it's not Score's theorem. It's not Score's theorem. So this is more general. So I'm not assuming these representations are discrete and faithful, for example. So this action doesn't have to be small. But there's always a unique minimal tree. And so the Corvar-Shane limit is always minimal for some reason. And that minimal tree is the one that has this as its length function. Okay.
So let's see. I think I wanted to say something else here about that. Yeah, okay. So this generalizes a theorem of Mike Wolf, or for Teichmüller space. So I didn't say that, but the Morgan-Shalen compactification, when you restrict to the Teichmüller component inside of here, is just the Thurston compactification of Teichmüller space. So it's sort of a generalization of the Thurston compactification. And in some sense, this theorem in that context was due to Mike Wolf earlier on. Okay, so so there's a compatibility, in other words, between this kind of combinatorial group theory stuff and the analysis, which is very nice. So one thing that's tying things together, especially here, is in the case of Riemann surfaces, is quadratic differentials. So from now on, probably I'll let X be a Riemann surface. And so QD of X will be the space of holomorphic quadratic differentials. Okay. So if I have a quadratic differential, which is not zero, the X for now, then I get an R tree. Which I'll denote T sub Q. And this is just the leaf space. Vertical or horizontal, I always forget which one. Let's say vertical leaf space of QD of Q on the universal cover. So I pull back my quadratic differential on the universal cover, and now it's got transverse measured foliations. And if I take one leaf space, then that becomes a tree. And the transverse foliation gives me a way to measure distances along that tree. And so this is sometimes called the dual tree to a measured foliation, and a quadratic differential gives you a pair of measured foliations. So this is called a dual tree. And what was noticed really by Mike Wolf was two things. So one thing is that if I look at just the projection onto the leaf space, this is harmonic. He actually kind of took this almost, I mean, he didn't quite take this as the definition of harmonicity, but this was even before Corvair and Schoen. And, but one can show a posteriori that his definition of harmonicity agrees in this case. So this really is a harmonic map. And conversely, so an equivariant harmonic map, right? So there's a group acting here and the group acting on the tree as well, because it came from a quadratic differential that's invariant here. So conversely, if I have an equivariant harmonic map to a tree, then I have the Hopf differential for this map. I think I talked about that before. And this is actually holomorphic. So there's enough regularity, again, from this kind of Gromov-Schoen argument or whatever. Actually, you don't even need the full force of that, but there's enough regularity to show that the Hopf differential, which only makes sense sort of away from the vertices, actually extends as a holomorphic quadratic differential on H2. So there is this holomorphic object associated to any harmonic map from a Riemann surface to a tree. So let's let this be Q. And then the theorem is that, well, the statement is that H2, this harmonic map, factorizes through the dual tree to the quadratic differential, where this is what's called a folding of trees. So folding is where you take two edges and you identify them. So it's kind of a structure theorem for harmonic maps to trees. Yes. It's a little bit, so folding is going to come up later. That is one source of non-uniqueness.
But even in the case where you have uniqueness, you could still have folding. So even when these trees are completely well-defined, they don't necessarily have to be dual trees to quadratic differentials. Okay, so here, let me just make sure I'm saying everything that I wanted to say. Yeah, okay. So so now this is so now we see Higgs bundles coming in. So let's let MH of X be the moduli of Higgs bundles. Rank 2 trivial determinant Higgs bundles. On X. And so here I have the Hitchin map to the space of quadratic differentials. Any rank 1 group will work. Yeah. We didn't actually write it that way, but yeah, it's the same thing. Okay, so here we have the Hitchin map to quadratic differentials, and the Hitchin map, I don't know if it's been stated at some point, maybe I said it, but the Hitchin map, in this case, the image of the Hitchin map is the Hopf differential for the corresponding harmonic map from Forlet's okay? Up to some scaling or whatever. But this is really the Hopf differential map. So fortunately, Hitchin and Hopf both have the letter H. So we can define a dumb compactification of the Higgs moduli space. Namely, I just take M Higgs, and I take the union of the boundary of the sphere and infinity in quadratic differentials. Now, on the other hand, we have the non-abelian Hodge theorem that says that when I look at M Betty, this is a homeomorphism with M Higgs, right? Homeomorphism. Homeomorphism. And on the Morgan-Shanlin compactification, I can extend this to a map, to my dumb compactification. So what do I do at a point here? Well, remember the points in the Morgan-Shanlin compactification are defined by R trees. I can take the harmonic map to that R tree, and I can take its Hopf differential. Okay? And that's the map on the boundary. So there's a little bit of subtlety here because, as I said, the tree is not always uniquely defined, and so one has to be careful that that's a well-defined map, but it is, actually. And so then the next theorem, again by the same characters here, is that this map is actually continuous. So this map, whatever it's called, F is continuous. Moreover, restricted to the discrete faithful representations, to the closure of discrete faithful, it's a homeomorphism. So, so this is, again, a generalization of Mike Wolf's thesis, actually, where he showed that the harmonic maps compactification of Teichmüller space is the Thurston compactification. So the point of this is that that extends actually to the Morgan-Shanlin compactification. It's just that there are some points over here that are going to have fibers. And the fibers come from this folding that I was talking about over here. Okay? So this is kind of a subtle issue. There's a big industry right now, as you probably know, to understand for, let's say, the SL3 character variety, to understand the limits. So Anne Parot has sort of extended the Morgan-Schälin compactification in terms of generalized length functions, and Kaczarkov and Simpson and Knoll and Pandit and others are working to sort of try to understand those generalized length functions as the translation length functions for group actions on some affine buildings. And so that would be kind of a generalization of this kind of picture. So, okay. So that's another application. And so finally, I want to give a real application to Higgs bundles. And so I don't have much time left, so this will be brief. But yes? Yeah. Yeah. Right. Well, I'll be agnostic about that. But in some sense, yes, there should be some sort of a relationship with. I'm not exactly sure how to answer that, but of course. Of course, the harmonic metric tells you about, the solution to the Hitchin equation, and somehow that's what this wall crossing stuff is also supposed to do. Given the quadratic differential, it's supposed to tell you how to construct. So maybe there's a back end kind of way of relating the harmonic map also to what they're doing, and in a way that you would sort of see this kind of stuff happening in infinity. But I certainly have not done that. Okay, so just to finish up, let me give maybe a little bit more of a concrete application to Higgs bundles coming from harmonic maps to truths. So let me ask a question. So this is a question that I first heard Hitchin mention, although he says other people have thought about it too, but I'll attribute it to him. And it's the following. So suppose I take a representation. Again, X is a compact Riemann surface, but maybe I'll write it that way. Let me let S be a closed oriented surface, just to free myself up from the Riemann surface here. So let's take a representation in SL2C. Okay, and let's assume that it's semi-simple because I'm always thinking of the modular space. Okay, and the question is, when can I find a Riemann surface structure on S, a Riemann surface structure on S, such that under the non-abelian Hodge correspondence, so M Betty goes to M Higgs, so my rho goes to something over here, to a Higgs bundle. When can I find a Riemann surface such that this lands in a fiber that's away from the degeneracy locus? Such that under this lies away from the degeneracy locus. The Hitchin fibration. So of course you could ask this for arbitrary groups. I do SL2C because that's where we have a theorem, but also because in SL2C it's rather easy to see what the degeneracy locus is. It's just those quadratic differentials that have some zero with multiplicity. Away from quadratic differentials that have zeros with multiplicity. So there are some obvious cases where you can never do this. So for example, if rho of pi 1 of s sitting inside of the isometry group of H3, if this thing fixes a point in H3, or leaves a geodesic invariant, for example, then the answer is no. And why is that? Well, if it fixes a point, then I have a harmonic map that's constant. In other words, that's a unitary representation, and the Higgs field is 0, and so the quadratic differential is 0, and sort of by definition, 0 is always in the discriminant locus. So unitary representations are always in the discriminant locus, so that's out. That can never happen. What happens if it leaves a geodesic invariant? Well, that basically will tell you that the Hopf differential is the square of an abelian differential. So in fact, I started out the lectures by writing down an example of a harmonic map where the harmonic map was just to a real line, and it was given by integrating a one form. And the Hopf differential is just the square of that one form. So there, every 0 has multiplicity. So those guys are also out. So those representations are. So these representations are called elementary representations. Okay. And so now the theorem is that that's the only obstruction. So the theorem of Mike Wolf and myself just last year is that there exists such an X if and only if the representation rho is non-elementary. Okay, so unfortunately I've run out of time, so I can't really explain too much about the ideas here, but suffice it to say that, that it involves looking at equivariant harmonic maps, not to H3, but to H3 across some well-chosen tree. And by allowing the complex structure on X to possibly vary, we can do it in such a way that we get what's called a conformal harmonic map, whose Hopf differential is 0, actually. And to say that the Hopf differential of this map is 0 means the Hopf differential for the map to H3 is minus the Hopf differential map of the map there. So if we can find a tree that has only trivalent vertices, for example, the zeros have to be simple zeros, and that works. So the real content of this theorem is to find this tree, and for that we use kind of rather powerful theorems, but in any case, it's an application again of harmonic maps of trees. All right, so I think I'll finish there. Thanks. Non-elementary means something that's neither one of these two. So what it means more precisely is, so rho semi-simple again, let's assume rho is semi-simple, is elementary if it's unitary, so conjugate into the unitary group, reducible, or conjugate into the subgroup generated by something of the form lambda minus lambda for lambda and C star, and minus 1, 1. So this leaves a geodesic invariant, but it has a reflection inside of it. So that's, strictly speaking, that's not reducible, but it still leaves a geodesic invariant. So those are elementary, and then non-elementary is anything else. Sorry? So these guys could be reducible. So this is not exclusive, if that's what you meant. Oh, this is not reducible. Oh, yeah. Okay, yeah. Yeah, probably. Yeah. Yeah. Yes. Yeah, right. Good question. Thank you for asking that. So it gets much more complicated as soon as you go to other groups. So for SL3C, rank one. Rank one. I don't know offhand, but yeah, we probably should have done that. I don't know offhand, but I imagine that it's probably, well, I don't know, but our proof would not work. Yeah, so I shouldn't say anything. Well, I don't know. But the the other component. Yeah, I don't know. I think our proof wouldn't work. But. I mean, you're saying that you can reduce it to this case. Yeah. What I'm worried about is a map to SO3 in the other component. So there our proof doesn't work. It's probably true, but our proof doesn't work. No. So in fact, I was going to reference Lauer's thesis here. So if you go to higher rank groups, then there are lots of other obstructions coming from looking at basically what Lauer was talking about before. Sometimes in subgroups, in some groups, you're just always in the singular locus, and so somehow you have to stay away from those. And we don't even know how to build the right conjecture about what should be true there. But so actually, I must say we don't have any idea how to generalize this.